Thank you. It's a pleasure. It's a pleasure to be here. Thank you for the invitation. I remember when we first did equation free, there was a meeting here at the Fields. It was in a different room, a different building, but I remember visiting then. So there's a lot of people, so I'm kind of going to take you through a bunch of years and a bunch of results and experiments and so on and so forth. In terms of the people, Tom Bertalan down there is a postdoc that works with me who happens to be here. And among the many senior people, I wanted to mention Bill Gear, who passed away this year and was a very good friend and collaborator. So I like this slide. I stole it from Julio Tino at Northwestern. Simple systems, a few degrees of freedom. Complicated systems, many degrees of freedom, but each one is supposed to do a particular job. Complex systems, many degrees of freedom, more or less interchangeable, many fishes, many people, many molecules. And somehow order emerges from the interactions. Otino's point was complicated is different than complex. My point is this looks simple, but it really is complex because there's many molecules in a ball. And it is only because we can model it effectively for billiard playing purposes in terms of a sphere with a center, a mass, a radius, a coefficient of restitution. It's only because we can model it usefully that we think of it as simple. I think more or less everything is complex. This is my favorite equation-free example. It comes from the work of Tony Roberts, who is a really smart guy, an Australian mathematician. It's a model of plankton. These are two views of the same thing. You just heard again from several talks also about micro and macro. So on the left is micro, on the right is macro. Let me play it a little bit. You see a bunch of microorganisms. They give birth, they die, they're swished around by the ocean. On the right, it's the right macro variables, which here happens to be G of R, the pair correlation function. This looks like hell. You can only simulate it and look at it. This will look like a partial differential equation that goes nicely to a steady state. If you could write a closed problem for the G of R, then all of the tools that we know and love, integration, stability, control, optimization, whatever can be applied. Well, on the simulation on the left, you can just run it and look at it and describe it to your friend. So it's important to know what are the right variables and what is the operator in the right variables. And Pantelis already kind of talked to you about coarse projective integration. If I have equations at the micro level, but I don't have equations at the macro level, then I run a little bit. And what I would get from a macro formula, I get from a judicious short experiment and estimation from the micro simulation. So I run the micro, observe it on macro, estimate time derivatives, estimate actions of Jacobians, estimate coarse derivatives with respect to parameters. And here we are doing just an Euler jump, but we also, in all of the equation-free stuff, we can do Newton-Krylov for fixed points and eigensolvers, coarse fixed point solvers, and so on and so forth. And he already mentioned the adaptive part. If you integrate, how do you do adaptive steps? You do the step you do a projection one step and half the step estimate the macro error. That's at least one way that we are taught in numerical analysis on how to adapt. But the important thing, okay, equation-free is a misnomer. You have equations at the micro scale. It's at the macro that you don't have them. Variable-free, which is much more important, how do we know what's the right thing to observe? How did I know that it was the pair correlation function? I knew it because I read the paper by Roberts. But if I have a cloud of points, I could take a lot of moments. At some point, I would have enough maybe to do a good description. Or I can have a lot of experience with a problem, or I maybe know enough math to be able to go from the Boltzmann equation to the Navier-Stokes, or to go from individual E. coli motion to bacterial chemotaxis. So whether I understand it or not, maybe my brain or some other person's brain will do the data mining and find the right observables. And for the last 20 years, actually to be fair, for the last 130 years in terms of principal components, but the last maybe 20 years for isomap, local linear embedding, diffusion maps, and so on and so forth, we can kind of use manifold learning algorithms to find good observables in terms of which to derive equations. So as I said, principal component analysis for 130, I think, years. And now this is my, you see, it says here, you see in the third line, it says non-linear principal components. So we wrote a paper in 1992. I'm going to tell you some ancient history in which we used the results from a paper from 1991 by a guy whose name was Mark Kramer, a very smart guy, assistant professor in chemical engineering from MIT. He didn't get tenure at MIT. He, as far as I know, discovered autoencoders. He called them nonlinear principal components, bottleneck neural networks. You take 40 variables, you boil them down to 3. You teach this the identity, you get back the 40 variables. So this is something that it's something that we used, and this is what happens when you get old. We used it, and then we used to hate it because this was a nonlinear, non-convex optimization problem. It would run for 2 weeks. If it failed, you didn't know if it failed because you had a bug, because you initialized badly, because the problem was not reducible. If it crashed, you have to run again for 2 weeks. So it was wonderful when it worked, and you didn't know what to do if it didn't work. Now things work much nicer. So we used autoencoders in 1992. I will show you an example in order to get the macro variables in terms of which we were going to make surrogate models. And then my particular poison is neither t-SNE nor local linear embedding. I use diffusion maps in part because I work with Rafi Koifman. So here is this paper in which we got data-driven equations from experiments from a single time series, parameter dependent. You know the statement, the old curmudgeonly professor says, all of this is wrong, and I published it first anyway. So it has a horrible title, Discrete versus Continuous Nonlinear Signal Processing of Copper Electrodissolution Data. It actually involved experiments with Jack Hudson, who took copper and put it in hydrochloric acid and dissolved it. And what he found was that depending on conditions, you see there's a number up there in volts, you could have a constant time series, so the reaction rate, the dissolution rate was constant, then it was periodic, then it was complicated periodic, and down here are the reconstruction with Takens time delays, steady state, limit cycle, period doubling, period quadrupling, and chaos. And so the point is, we have parameter-dependent single time series. How do we get surrogate parameter-dependent models? And so what we did in 92 was to look at the Runge-Kutta and realize that the Runge-Kutta is a recurrent resonant. That is, if you have discrete data, yn plus 1, you take this, you pass it through a network, you get something, f. You take this, you add it to the initial condition, you pass it through the same network, you get something else. Take it and add it to the initial condition, pass it again 4 times, and then at the top, you see it's a resonant. You don't fit yn plus 1 as a function of yn. You fit yn plus 1 as the correction from yn. And if you look at it a little bit carefully, maybe you will recognize a sort of Krylov subspace type of iteration. I have something and I evaluate it, and then I perturb it a little bit and evaluate it, and perturb it a little bit and evaluate it again. And then I do something that lives in the span of all of these little perturbations. So there is a sort of matrix vector product estimation. I hope you see what I'm saying. If not, take my word for it, or at least take it under advisement. But the idea is that, and that's something that I tend to think a lot more as time goes on, that interesting architectures like resonance or recurrent networks or whatever, if you look at them enough, then you will recognize under them an algorithm from traditional numerical analysis that we know and love. And this is the resonant paper, which is 2015. It's just forward Euler. I think it has already been mentioned. Again, the idea is that you learn something which, when integrated with forward Euler, would give you the result. And I laugh at myself when I tell you that the recurrent Runge-Kutta resonance from 1992 have a very respectable 100 citations, and this has 150,000 citations by now. Where do the right variables come from? I already told you about Mark Kramer's paper in 1991. So what we had is that we had long time series on one variable. We took the long time series and we did autoencoders. We got 3 nonlinear principal components, so 3 coarse variables. And then we used this Runge-Kutta resonant in order to learn the right-hand side of the equation as a function of the parameter. And here is some of the time series reproduced, some of the attractors reproduced, and some of the bifurcation diagrams reproduced. And those of you that care about details in nonlinear dynamics would know that period doublings are generic for continuous dynamical systems, but period doublings are not generic for discrete dynamical systems. You don't have tori that period double. They disintegrate before they break into 2. And so if you use a traditional time one map fitter, it could be an amazing fitter, but all the wrong term dynamics and all the bifurcations would be qualitatively wrong. It's a fun issue. And we use this idea of taking numerical algorithms that we know and love. So up there, you now see Crank-Nicolson. Crank-Nicolson is implicit. So this is an implicit neural network. To evaluate it, you need to solve nonlinear equations. And another thing that we played with was gray boxes. That is, if we needed to learn a model where a whole bunch of the terms were known, but one was not known, then we would hardwire the physics and we would only learn the part that is not known. And then this is 1993. This is movies from carbon monoxide oxidation on single crystal platinum in high vacuum. The colors that you see, there's more oxygen when it's red and more carbon monoxide when it's blue. We got a VHS tape, we digitized it, we got all of the movies, we did principal components on the movies, we got 4 principal components. And then, using these empirical basis functions, the problem became 4 time series. So we used neural networks with histories, with delays, in order to learn the time one map of these time series. And then what we could do is that we could reproduce the attractors and we could reproduce the movies. This is taking PDEs, getting empirical basis functions, reducing them based on the empirical basis functions, and then learning approximate inertial forms. That is, learning reduced ODEs on the slow manifold of the PDE. These were the attractors. This is from experiments with Bob Ecke. This was in Physica D, 1994. What you see up there, you see these invariant circles. These are Poincaré maps from Rayleigh-Benard convection in, God help me, superfluid helium. What we did is that we took the time series that came from the observations with delays and the Rayleigh number, and we used these in order to parametrically reconstruct the bifurcation diagrams from the experimental data on Rayleigh-Benard convection. Those of you that play with quasi-periodic systems would recognize the phase lockings and the devil staircases that come up in problems like that. A little more ancient history. So in 1998, what we did is that we again used numerical analysis to learn partial differential equations from data. Think of a parabolic PDE like the KS that Pantelis talked about and a lot of other people during these days. So it's a relation between the time derivative, the function, a few spatial derivatives, you have to decide how many, and the parameter values. So what we did is that we got back then data from the Kuramoto-Sivashinsky, and then we took data on a few nearby points, a finite difference stencil. We used finite differences to estimate derivatives, and then we used a neural network to learn the relation between parameters, the function, derivatives, and the time derivative. And then what we did is that we took all possible shifts of this. So this is a convolutional neural network. And we combined a convolutional neural network in space with this, remember this recurrent Runge-Kutta 4 steps in time, so that you would have discrete space-time data, and you would use it to learn to approximate the right-hand side of the PDE. And that is a spatiotemporal limit cycle of the Kuramoto-Sivashinsky from the simulations and from the recurrent model that was learned from the effective PDE that was learned this way. Again, the main point in all of this more than anything else is finite differences are, in some sense, convolutional neural networks. So again, ideas that are very useful, we kind of find that they have a root, I believe, in the algorithms we know and love. Okay, so much for ancient history. Here is a problem where you have microscopic stuff, but you believe there exists a macroscopic PDE. So you run microscopic simulations, learn a macroscopic PDE. My relatively recent example is playing with E. coli chemotaxis. It's a beautiful system. Hans Othmer, who is a friend from Minnesota, has a model for an agent-based model for the E. coli. Each one of them has a couple of internal states that are governed by ordinary differential equations. And then there's a number of stochastic integer variables, 0 or 1, that have to do with whether the flagellae are going clockwise or counterclockwise. And what I'm going to show you is just one little movie. Here is 5,000 bacteria that are moving in one dimension. This is the food, so they want to go towards the place where there is more food. They are blue, green, or red or yellow, depending on whether they're going to the right, they're going to the left, or they are tumbling in place. And what you're going to see if I play the movie is that you can get the data from the agent-based problem. And if you know that the right variable is the density of the bacteria, then in red, you see the PDF of the agent-based model, and in blue, you see the evolution of the learned PDE on the bacterial density. So this is, if you want, learning the right-hand side of chemotaxis. This is exactly the same thing. The difference is, you see at the top, it says gray boxes. So if I know the diffusive part from experiments without any food, then I can hardwire the diffusive part and only learn the chemotactic part. And if I play this movie, again, it's going to kind of look pretty good. So the idea is, take solvers that you understand. Rongekuta, finite differences, spectral methods, whatever, and then create neural network architectures that embody these. And this is something more recent, done with Felix Dietrich. Let us now consider that we have, again, discrete time data. We heard a couple of very nice talks about learning SDs from data. And now what we want to do is that we have a neural network that is templated on an Euler-Maruyama, a Milstein, a Hoyne, and then estimate the drift and the diffusivity of the SD. Where does the numerical algorithm go? It goes into the loss scheme. This was already said. And this is a little example where we run some SIR on the lattice. So there is blue, yellow, and green. It is known that at some limit you get effective ordinary differential equations. At smaller lattices you get effective stochastic differential equations. So we learn the effective ordinary and stochastic differential equations. This is still trying to get published, but it has been for a couple of years on the archive. Okay, so I told you about no equations and no variables. This is just a little taste of no parameters. We all work very hard on reducing the state of dynamical systems. What about reducing the number of parameters, finding what the effective parameters are, not look at viscosity and the diameter of the pipe and the pressure drop separately, but look for a Reynolds number if you want. I am overselling it a little bit. Here is a very simple example. You have two parameters, P1, P2. The output is the product, P1 times P2. So there is huge level sets on which the behavior is the same, but the parameters are different and give you the same behavior. This has to do with parameter identifiability. So there's a paper that just came out. It's called On the Parameter Combinations that Matter and Those That Do Not. Okay? And so what's the idea here? If you perturb the parameters and look at the response, you will find that even though you're perturbing two parameters, there's only one dimension in which the response changes. So by perturbing all parameters and looking at the cardinality, if you want, of the response, you can figure out how many combinations of the parameters matter to the response and how many don't matter. And after you do that, this is my little example. Let me kind of skim over it. It's a problem that has several parameters, but there's only one effective parameter. So bear with me. What we do is that this is a simpler example. You can see this has 3 parameters, but there's only one effective one. So if you take an initial condition and you look at the response of the system in all possible kicks, you're going to find that there is a 1 parameter family of responses. And then we can either do it with diffusion maps as an eigen problem, but this is cute. It is what we call a local conformal autoencoder. Words. What does this really mean? I have 3 parameters. And this is an autoencoder that takes the 3 parameters and gives me the 3 parameters back. But I have done this data mining and I figured out that only one combination of the parameters matter. So what do? I take one of the middle neurons and use this neuron to learn the output. And then the other 2, I ask, this is the conformal part, I asked for the other 2 neurons to be locally conformal, orthogonal, to the neuron that fits the response. So I can take the neuron that fits the response, and then the rest of the neurons are parametrizing the level set. That's the thing that you see on the top right. There is the direction in which the output changes, and then there is the direction in which the output does not change. And so by doing this, we can find the number of parameters that are necessary to predict the output, and then the number of parameters that are not identifiable, so that if we run along this level set, then the output remains the same. Okay, this is a little bit about no parameters. How about no space and no time, which is kind of the fun part I'd like to think of today's talk. In 2011, I think, the DARPA had something that they called a Shredder challenge. What they did is that they took 5 documents. One was this, there was a typed memo, there was a sketch of a building or something. They shredded them, they put the shreds on the web, and then they promised $50,000 to whoever would be putting back together again. It took a month, I think, for a company from California to do it. My students and your students and those of you that are students in general can do it these days with, I don't know, in 15 minutes. What's the basic idea? Here it is. Here is a PDE, a one-dimensional in space PDE in time. It has some messy patterns in space-time. What you do is that you take this output as it comes out of the printer, you take it to the office. You understand, the last 2 years we did not go to the office. So now I can say again, you take it to the office and you put it through the shredder. And what you're going to do is that you're going to get 512 time series. And you take these 512 time series and you mix them up. So you don't know where they come from in space anymore. The picture looks like a mess. But you've all solved puzzles when you were kids, and you have kids maybe now that solve puzzles. What do? You take all of these data points and try and organize them so that somebody lives close to somebody similar. You use smoothness in order to be able to reorganize the data. And indeed, if you take these 512 time series and do data analysis when they're scrambled, you find that there exists a one effective parameter for the variability. And if you order them along this parameter, you find that what you have is 1-to-1 with the original space. Actually, it's flipped, because the algorithm that uses smoothness does not know who is on the right and who is on the left. So what's the idea? You have data in space and you mess them up. You do a little bit of data mining, and then you can find a space which is homeomorphic, diffeomorphic, the same, is stretchable into the original space. Same idea in 2 dimensions, X and Y and time. This is a Ginzburg-Landau. You take this space-time behavior, you push it through a meat grinder, you get 40,000 strings of meat time series, and then you do data mining on them, and you find that there is a 2-parameter variability. These 2 data-driven variables are coordinates in which it makes sense to plot the behavior so that it is smooth. So we don't have space, we have behavior, we analyze the behavior, and we figure out what would have been a good data-driven space. We use the word emergent space because physicists use the word emergent space in which to plot the data. And here is something that is closer to the heart of a lot of people. This is 800, if I remember correctly, Strogatz amplitude and phase oscillators. They're all coupled. They're all but they're all a little bit different. And I have colored them by a magical color, and if I run them, what you will see is that they very quickly organize themselves along a one-dimensional geometric curve, and as time goes on, they do all kinds of stuff, but this ordering along this one-dimensional space kind of remains the same. And if you were going to keep as a variable the relative arc length along this curve and plot things as a function of this emergent space variable, then if you looked at the behavior would look like, oh, why don't you play? You don't like me. It would look like a partial differential equation. So here I am plotting the behavior as a function of this data-driven coordinate, which in retrospect, if you happen to know how heterogeneous they are, you find that this data-driven coordinate is 1-to-1 with the heterogeneity of the data. So you have these oscillators, you don't know that they're different, but you actually find out by looking at their behavior, it's not so surprising, that there exists a 1-parameter variability along them, and therefore a 1-parameter variability in their behavior. This is a maybe not so easy to understand in detailed picture, but it's kind of cute. It's the same idea. You run these 800 oscillators, Each one of them is a point down here, but if you don't plot them as points down here, but you plot them in terms of this data-driven coordinate, then you will see that in this data-driven coordinate, they look like nice partial differential equations. So the idea is that you look at the behavior, which is messed up, you analyze the behavior, same thing again. If you color them by where they started, they are not very much in order, but if you take each one of them and study them, the first one up to the 200th one, they look like a tangle of spaghetti, but if you look at their behaviors and do data mining on their behaviors, you will find that there exists a rearrangement, an emergent spatial coordinate in which they look like a nice field. And then you can go and learn the PDEs in this emergent space. So this is just to say that when you plot them in this variable, the behavior in space-time looks smooth. You go into this space and now you learn a partial differential equation in terms of this emergent variable phi1. And we did this as a function of the parameter, and we can find that indeed, as you change the parameter that has to do with how broad the distribution is, you can go from uniform eventual stationary solutions to spatiotemporal oscillations. Again, the main point here is that the space in which we learn the model also comes from data mining. This is a two-dimensional problem, and this is something that was our pride and joy when Tom, who is back there, first did it. What you see here is 1,024 neurons. There are 1,024 computational Hodgkin-Huxleys. They are heterogeneous because their parameters are heterogeneous. They're also heterogeneous because they're connected in a chung-glue network, not in an all-to-all or something like that. So they are doubly heterogeneous intrinsically and structurally, just to kind of make it sound impressive. Each one of them does something slightly different, but if you analyze all of these 1,024 limit cycles, you find that there exists a two-parameter variability, and this network can be thought of as a spatial discretization of a very nice domain in a set of coordinates that comes from mining the data themselves. So again, the idea is, if there is no space, look at the behavior, and it can tell you the space in which the behavior will look smooth. We were so happy when Tom first got that movie. Instead of having 1,024 spaghetti-like time series, if you plot the behavior in these coordinates in time, then it looks like a smooth field. It looks like a flag. We're calling it the flag flapping in the wind. It is a good space in which to learn a reduced model. And in what I told you up to now, it was the space that I shredded and reconstructed. You can also take time and shred it and then reconstruct it. Or what you can do is that you can take little space-time chunks and mess them up. And this is really like a puzzle, and put it together again. There is lots and lots of nice papers, especially the last maybe 5 years, on puzzle reconstruction. The idea is that the algorithms for puzzle reconstruction are precisely the algorithms that give you a good emergent space in which the behavior looks nice. Nice in this case is smooth, so that one can learn a PDE model for it. This is kind of I paid for this. I don't know if it was worth it, but think of this two-parameter family of data. There is color in one direction and phase of growth in the other. You take this, you mess it up, and then by doing the right data mining, if you want, you can find that the data are a two-parameter family of data. There is some interesting twists of which is a time-like direction and which is a space-like direction. And you can reconstruct it and then learn an evolution law, if you want, in this figure. And in what I've told you, the idea so far was sit at particular places in space. This is a modulated traveling wave for the KS. Whether you sit at different moments in points in space and take little time series, whether you sit at different points in space, God help me. Different points in space get little time series. Different moments in time take little snapshots. Different little patches of space-time. Even taking moving observers, as long as they don't run into each other. All of these different measurements, there is a way of taking them and fusing them and finding out that all of them would reconstruct on the same torus, which is the modulated traveling wave of the KS. So the idea here is matching, fusing different observations of the same thing. This is a caricature. I wish I had thought of this, but this is something that was taught by Koifman and Singer in 2008. And this is my caricature version of it. let's say that there exists we have different views of something, and there is one divine or Platonic view, the correct view. So this is the intrinsic space. Then on the one side is Yannis' space, and on the other side, since Boumediene invited me, it's Boumediene's space. And how do we observe and do data mining? If in Platonic space, we take data, and since Boumediene likes kernels, we use the distance between the two and put them in a kernel so that we can do data mining of all of the pairs of points. Now, I am not as perfect as Plato. I have an observation function which is not a diagonal. I see things a little bit distorted. The main idea is that when we work in this Koifman and Singer context that involves what's called the Mahalanobis metric, I don't only observe the point, I also observe a jiggle around the point, a little bit of a covariance of a noise around the point. And the idea is that while in Platonic space I always have the same jiggle, when I observe it, this perfect jiggle will get distorted, and the distortion is going to give me an idea of the local distortion of my glasses. And by stitching together all of these local distortions, so this is diffusion maps with the Mahalanobis metric, I can actually map what I see to Plato. And Boumediene has his own way of looking at the world, and he has his own observation of the covariance of the noise. But this structure, the way that I did it, you see that it looks a little bit like a lens. It allows me to go from me to Boumediene by reference to a normal form, to a Platonic space where the covariance of the noise is z-scored. You can do this by diffusion maps and eigenproblems. This is the anisotropic diffusion maps, as it is called by Koifman and Singer in that original paper. There is a lot of development since then, but what we did a couple of years ago is to create this. This is a different local autoencoder, local conformal autoencoder. What you do is that you take data and the covariance of the noise around them and try to find the transformation. This is just to make sure you don't lose any data. Try to find the transformation in a space where when you embed the data there, the noise becomes z-scored. So it's trying to look at the data with extra information. You don't only get the data, you get the data and a jiggle around the data, and then you can create a normal form picture of a Platonic space for the data, if you want. This is an illustration of this that comes from the paper of Singer, the first and the top. You take data on this perfect square. This is a distortion of the data. This is another linear distortion of the data. The idea is that when you look at these two, if you do data mining on them, as I briefly outlined now, then they will both become squares, and it takes only a rotation and only takes an orthogonal transformation to map one to the other. So you can take very different observations of the same thing, and with a minimal number of joint pieces of information, you can map one to the other. You don't have to do optimal transport if you want for Wasserstein metrics. We've played on this. How do you look at different cameras that look on the same thing? This is not, now I'm going to kind of tell you a couple of funny things. This is literature. Since we cannot change reality, let us change the eyes with which we see reality. This is from Kazantzakis, a Greek author, first half of the 20th century. This is trying to be funny using words from Cole Porter. This is the Little Prince. You only see well with the heart. What is essential is invisible to the eyes. I'm kind of trying to make jokes about the fact that maybe the right space in which we should observe the data is not the space in which we see them, but a distortion in which the behavior makes more sense. This is the same idea, a flow box theorem. Take trajectories of an Arnold-Beltrami-Childress flow and flow box it, make it straight lines, and then be able to take it back again. And then again, trying to be playful, Dora Maar was one of the muses of Picasso. This is how Picasso drew her. This is how Man Ray photographed her. The idea is we should be able to match, rectify, as in some work that we did with Felix and with Eric, who is here, try to match different observations of the same thing. And let me see. So I start to, okay, honestly, how much time do I have? 2-3 minutes. Okay. In the 2-3 minutes, let me kind of go over the extra art stuff. You can ask for it if you want. and tell you something that is a little bit science that we're doing now. Okay, so here I dug up, oh, this is not the right one. Okay, so 1902, Damar wrote a very influential paper. So this has to do with doing well-posedness through data-driven techniques, okay? How do you use data mining and machine learning to figure out if a problem is well-posed or not? And this was 1902, as I said, that Damar wrote a paper which for some reason appeared in a journal called the Princeton Bulletin. And he starts, first he has something by Poincaré, and then he says, the geometers pose themselves two problems, the Dirichlet problem and the Cauchy problem. And these days, we don't get data at the beginning and on the sides. We can data in the middle of a domain. We can have many little batches. We can have lots and lots of little pieces in the domain in which we have data. And so if you're going to solve an equation, in this case, let's solve it with pins, physics-informed neural networks. You can think of it as collocation on neural network basis functions. This is the word of George Karniadakis. It started by Lagaris and Fotiadis in 1990-something, but it has exploded recently using machine learning tools and software and ideas and new algorithms to solve partial differential equations in a different way. How do I know that the problem is well posed? And I will give you a very simple idea. Here is again the modulated traveling wave for the Kuramoto-Sivashinsky. Let's say that I don't know the equation, but I have data on this space-time corridor, on this space-time corridor, and on this little chunk. And since you know it's a parabolic equation, you can kind of see that in here, it'll be a well-posed problem up to the top of the domain. The idea is that if I take such a problem, and bear with me, and I solve it in a bigger domain. Please notice again, I prescribe initial conditions, I prescribe data in these corridors, and then I solve using pins, the PDE, in this big T-shaped domain. What's going to happen? I'm solving the PDE variationally. In the part of the domain where the problem is well posed, every time I solve variationally, I'm going to get the same solution. In the part of the domain that is not well posed, every time I will solve with a different initial condition variationally, I'm going to get a different solution. And this is indeed what happens. If you look, you will find that all the parts in the well-posed part, you always get the same thing, but on the non-well-posed part, you get different things. So this is an idea. How can I use this idea to determine well-posedness? Let me give you one simple example, and I will kind of stop there. Think of a very, very simple linear ordinary differential equations. It's second order. So you need two data points, like two boundary conditions. Usually, we never solve the problem unless we know it's well posed, unless we have enough boundary conditions. Suppose that I have no idea how many boundary conditions I put. If I solve this problem with two boundary conditions, I'm going to get one solution. If I solve this problem variationally with one condition, what am I going to get? Humor me. Every time, there is going to be a one parameter family of solutions, yes? So every time I solve it, I'll get something else. So what I do is that I solve it 1,000 times, and I get 1,000 solutions, and I do data mining on 1,000 solutions, and I figure out either with principal components here or with diffusion maps that I have a one parameter family of solutions. Therefore, I need one more initial or boundary condition. And let me show you just one beautiful picture, for me, beautiful picture. What you see here is the wave equation. And in this problem, instead of giving initial and boundary conditions, I prescribe the solution on a little parallelogram in space-time. And I solve variationally many, many times, one time with no other conditions, and one time with a reflecting boundary condition here. What you see plotted out there is the variance of the many solutions. The part that is well posed, which you see is delineated by characteristics, you always get the same thing. And the variance of the many solutions is practically zero. In this problem, because of the reflection, this problem here, this corridor, also has two characteristics. So the idea is that by analyzing the many solves, you understand this is a stupid thing. Instead of trying to make the problem well posed and solve it once, you take it, whatever it is, willy-nilly, you solve it a bunch of times, which is very easy to do these days, and then you analyze the results, and you kind of have to trust me that if you analyze the results, not only can you find what are the parts that are well defined and the parts that are under-defined, but there is also ways of looking at the under-defined parts and figure out if there is one characteristic, if there is 0 characteristics, and so on and so forth. Basically, what I'm telling you is a simple idea. By solving many times, which now we can afford to do, and analyzing the results, it is possible to explore experimentally in a data-driven way well-posedness for a problem. It's much more difficult to do the overdetermined problem. When you do the overdetermined problem, you run out of time and people look at you in a nasty way. This is a place, just one, if you have an overdetermined problem, then techniques from randomized linear algebra, where you drop randomly equations and try to figure out how many do you have to drop to have a well-defined problem, become useful. So I personally find it nice that there is a link with randomized computation. Thank you. That's it.